Welcome back. Over the last two episodes, we learned what eigenvalues and eigenvectors are, and how to find them with the characteristic polynomial. An eigenvector is a special direction that a matrix only stretches, never knocks off its line, and the eigenvalue is the stretch factor. Today we collect the reward. The central fact is this. If a matrix has enough independent eigenvectors to fill the whole space, then it is secretly a diagonal matrix wearing a disguise. We can write A as P times D times P inverse, where the columns of P are the eigenvectors and D as a diagonal matrix holding the eigenvalues. We will see exactly when this is possible, why it makes powers of a matrix almost free to compute, and how it hands us a closed-form formula for the Fibonacci numbers. This is the episode where eigenvalues start earning their keep. Let's recall the setup in one slide. A non-zero vector v is an eigenvector of a matrix A, with eigenvalue lambda, when A times v equals lambda times v. In words, feeding v through A does not turn it off its own line, it only scales it by the factor lambda. We found these in earlier episodes by solving the characteristic equation, the determinant of A minus lambda times the identity, set to 0, which gives the eigenvalues. Then, for each eigenvalue, we solved A minus lambda I times v equals 0 to get the eigenvectors. So far, we have treated eigenvalues and eigenvectors one at a time. Today's move is to gather the whole collection of them and use it to take the matrix A apart and rebuild it in a far more convenient form. That rebuilt form is the diagonalization. Here is where P and D come from, and it is just bookkeeping. Suppose our n by n matrix has n eigenpairs, eigenvalue lambda 1 with eigenvector v1, and so on up to lambda n with vn. Build a matrix P by placing those eigenvectors as its columns side by side. Now look at A times P. Matrix times matrix works column by column, and A hits each eigenvector by scaling it. A times v1 is lambda 1 times v1, and so on. So A times P is the same collection of columns, each multiplied by its eigenvalue. That is exactly what you get if you take P and multiply on the right by a diagonal matrix, D holding the eigenvalues. So A times P equals P times D. Finally, if the eigenvectors are independent, P is invertible, and multiplying both sides on the right by P inverse gives the headline formula, A equals P times D times P inverse. So when does this work? The factorization needs P to be invertible, which means we need n independent eigenvectors, enough to form a basis for the whole space. We call that an eigenbasis. There is one very clean sufficient condition. If all n eigenvalues are different from each other, then their eigenvectors are automatically independent, and the matrix is diagonalizable. No further checking needed. Repeated eigenvalues are the subtle case. For each eigenvalue, you compare two numbers. The algebraic multiplicity is how many times it appears as a root of the characteristic polynomial. The geometric multiplicity is the dimension of its eigenspace, how many independent eigenvectors it actually supplies. The matrix is diagonalizable exactly when these two numbers agree for every eigenvalue. When an eigenvalue is short on eigenvectors, the matrix is called defective. It has no eigenbasis, no P, and it simply cannot be diagonalized. Let's see a matrix where diagonalization breaks, so the condition isn't just abstract. Take the 2x2 with rows 2, 1, and 0, 2, an upper triangular shear. Its characteristic polynomial is the quantity 2 minus lambda squared, so lambda equals 2 is the only eigenvalue, and it appears twice. Its algebraic multiplicity is 2. Now hunt for eigenvectors. Solving A minus 2 times the identity times V equals 0, leaves the system with rows 0, 1, and 0, 0, which forces the second component to be 0. The only eigenvector direction is 1, 0. So the geometric multiplicity, the number of independent eigenvectors, is just 1, while the algebraic multiplicity is 2. They do not match. This matrix supplies only one eigenvector when it needs 2 to form a basis, so it is defective. There is no P, no eigenbasis, and no way to write it as PDP inverse. Geometrically, the shear has just one direction, it purely stretches. Every other direction gets tilted. It is worth pausing on what this factorization means geometrically, because that is where the intuition lives. When we write A as P times D times P inverse, we are saying that A and D are similar matrices, they are the very same linear transformation, just described in two different coordinate systems. In the ordinary standard basis, the transformation looks like A, tangled, mixing the coordinates together. But in the basis made of eigenvectors, the exact same transformation looks like D, pure, independent stretching along each axis. Read the product from right to left and you see a three-step story. P inverse translates a vector into eigenvector coordinates. D stretches each of those coordinates by its eigenvalue. Then P translates back to the standard basis. Similar matrices always share the same eigenvalues, the same determinant, and the same trace, because underneath, they are one transformation in disguise. Now the headline application, powers. Suppose you want A squared. Write it as PDP inverse times PDP inverse. In the middle sits P inverse times P, which is the identity and vanishes. What remains is P times D squared times P inverse. The same collapse happens for every higher power, so for any whole number, k, a to the k equals p times d to the k times p inverse. That would be a curiosity, except for one fact: raising a diagonal matrix to a power is effortless. You just raise each diagonal entry to that power, because the entries never interact. So d to the hundredth is simply each eigenvalue raised to the hundredth, sitting on the diagonal. That turns the hundredth power of A, which would normally be 99 matrix multiplications, into raising a few numbers to a power and sandwiching the result between P and P inverse. 3 small matrix multiplications. Done. Let this picture carry the whole idea. On the left, the transformation drawn in the ordinary standard basis. The grid lines stay horizontal and vertical, a circle of points gets pushed into a tilted, skewed ellipse, and the action looks complicated, coordinates clearly getting mixed together. On the right, the very same transformation, but now drawn on a slanted grid whose 2 directions are the eigenvectors. Along the first eigenvector, every point is simply stretched by the first eigenvalue. Along the second eigenvector, it is stretched by the second eigenvalue. No mixing, no skew, just 2 independent stretches, and the axes of the ellipse line up perfectly with the slanted grid lines. That is the entire content of A equals P times D times P inverse. Choose the right axes, the eigenvectors, and the only thing the matrix is doing is stretching along each one. P and P inverse are just the dictionary that translates between the 2 grids. Here is what powers actually do to a vector, drawn out. We have 2 eigenvector directions. Along the first, the eigenvalue is 2, so that component doubles every time we apply the matrix. Along the second, the eigenvalue is 1/2, so that component halves every time. Start with a navy vector that is a blend of the 2 directions, then watch its images under A, then A squared, then A cubed. With each step, the first component grows and the second component shrinks toward nothing. The result is that the arrows visibly swing around and line up with the first eigenvector, the one belonging to the larger eigenvalue, while stretching longer and longer. This is a preview of a deep idea. Under repeated multiplication, the largest eigenvalue in absolute value dominates, and almost every starting vector gets pulled toward its eigenvector. We will use exactly this when we study long-run behavior and Markov chains in 2 episodes. Let's diagonalize a concrete matrix, the 2x2 with rows 2, 1, and 1, 2. First, the eigenvalues. The determinant of A minus lambda times the identity is the quantity 2 minus lambda squared minus 1. Expanding gives lambda squared minus 4 lambda plus 3, which factors as lambda minus 3 times lambda minus 1. So the eigenvalues are 3 and 1. 2 different eigenvalues, so we already know it is diagonalizable. Now the eigenvectors. For lambda equals 3, solving A minus 3 times the identity times B equals 0 gives the vector 1, 1. For lambda equals 1, solving the corresponding system gives the vector 1, negative 1. Stack the eigenvectors as columns to get P. First column 1, 1, second column 1, negative 1. The diagonal matrix D carries the eigenvalues in the matching order, 3 then 1. And P inverse, for this symmetric P, is 1/2 times the same array of entries. We now have the full factorization. Now watch how cheaply we get every power of that matrix. We have A equals PDP inverse, so A to the k equals P times D to the k times P inverse. And D to the k is just its diagonal entries raised to the k, 3 to the k, and 1 to the k, which stays 1. Sandwich that diagonal between P and 1/2 times P, multiply the 3 matrices, and the answer comes out as 1/2 times a symmetric matrix. Its diagonal entries are 3 to the k plus 1, and its off-diagonal entries are 3 to the k minus 1. Let's sanity check with k equals 1, 3 to the first is 3, so we get 1/2 times the matrix with rows 4, 2, and 2, 4, which is rows 2, 1 and 1, 2, our original A. The formula is correct. And now the punchline. Want the 50th power? Just plug in k equals 50. Want the 1000th? Plug in 1000. No grinding through repeated matrix multiplication. Diagonalization gave us a formula for all powers at once. For the finale, let's solve the Fibonacci sequence in closed form. The rule is, each term is the sum of the previous 2. The trick is to carry 2 terms at once as a vector, the next term stacked on the current term. Then advancing one step is exactly multiplying by the 2x2 matrix with rows 1, 1, and 1, 0. So, the vector after n steps is that matrix raised to the n, applied to the starting vector 1, 0. Now we diagonalize. The eigenvalues come from lambda squared minus lambda minus 1 equals 0, whose roots are the golden ratio, 1 plus the square root of 5 over 2, and its companion, 1 minus the square root of 5 over 2. Raising the matrix to the n means raising those two numbers to the n. Reading off the top entry gives Binet's formula. The n, the Fibonacci number, equals the golden ratio to the n minus its companion to the n, all divided by the square root of 5. An integer sequence written purely in irrational numbers, and the square roots magically cancel every time. That is diagonalization turning a recurrence into a formula. Here is how far this idea reaches. Powers were just the start. Because a to the k equals p times d to the k times p inverse for every power k, any function of a that is built from a power series gets the same treatment. For a function f of a equals p times f of d times p inverse, and f of d is just f applied to each eigenvalue along the diagonal. The most important example is the matrix exponential e to the a, which is the engine behind systems of differential equations. Diagonalizing turns it into p times the diagonal matrix of e to each eigenvalue times p inverse. So solving the system x dot equals ax, the continuous cousin of a recurrence, becomes x of t equals e to the ta times the start, and in the eigenbasis, each coordinate simply evolves on its own as e to the eigenvalue times t. Diagonalization decouples a tangled system into independent one-dimensional pieces. A little history. The word eigen is German for own or characteristic. An eigenvector is a matrix's own private direction. The ideas grew out of surprisingly physical problems. In the 1820s, Cauchy studied the eigenvalues of symmetric matrices while working on quadratic forms and the stability of planetary orbits. In 1858, Arthur Cayley wrote his memoir on the theory of matrices, the work that first treated a matrix as an object in its own right, something you could raise to powers and invert. Then, in 1870, Camille Jordan answered the hard question lurking behind today's lesson. What do you do with a defective matrix that does not have enough eigenvectors to diagonalize? His answer, the Jordan normal form, is the closest substitute, nearly diagonal, with a few ones just above the diagonal to patch the missing eigenvectors. Weierstrass and Frobenius then built the full modern theory of multiplicities and canonical forms. Let's recap. To diagonalize a matrix A, we write it as p times d times p inverse. The columns of p are the eigenvectors, and d is the diagonal matrix of the matching eigenvalues. This is possible exactly when A has enough independent eigenvectors to fill the space, guaranteed when the eigenvalues are all distinct, and otherwise decided by comparing each eigenvalue's algebraic multiplicity to its geometric multiplicity. When the eigenvectors run short, the matrix is defective and cannot be diagonalized. The factorization says A and D are the same transformation in two different bases, so they share eigenvalues, determinant, and trace. The big payoff is powers. A to the k equals p times d to the k times p inverse, and powering a diagonal matrix just means powering each entry. We use this to write down every power of a matrix at once, and to derive Binet's closed-form formula for the Fibonacci numbers from the golden ratio. Next episode, the eigenvalues turn complex, and the geometry becomes rotation and spirals. Today we turned eigenvalues into a machine. If an n by n matrix A has n independent eigenvectors, we can factor it as A equals PDP inverse. The columns of P are the eigenvectors, and D is the diagonal matrix whose entries are the matching eigenvalues in the same order. This works exactly when there are enough independent eigenvectors to form a basis. For instance, whenever all the eigenvalues are different. A matrix that lacks enough independent eigenvectors is called defective, and it cannot be diagonalized. The real payoff is powers. Because P inverse P collapses in the middle, A to the k equals P times D to the k times P inverse, and raising a diagonal matrix to a power just raises each entry to that power. So a 100th power becomes a one-line computation. The same trick solves linear recurrences. The Fibonacci numbers live inside the powers of a 2x2 matrix, and diagonalizing it gives Binet's closed-form formula built from the golden ratio. Next episode, we face matrices with no real eigenvectors at all, where the eigenvalues go complex and the geometry becomes rotation and spirals. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.